Alright, in this video we'll be continuing with inductors in AC circuits, and in this video we'll be specifically talking about RL circuits, okay? So similar to our RC circuits where we have a capacitor and a resistor in series, in an RL circuit we're going to have obviously our AC supply, and we're going to have a resistor in series with an inductor, like so. Okay? And again, just like our RC circuits, we're interested in the phase relationship between the voltage across the resistor, the voltage across the inductor, and the voltage of the supply. Okay? So we have our voltage of our supply, and again, this is the RMS value. We also have the voltage across our resistor, and once more, this is again the RMS value. And we have the voltage across our inductor, which again is the RMS value. And just like our RC circuits, we realize that when we add up our voltages, Kirchhoff's voltage law seems to be broken at face value. And so what I mean by that is that the Vs, which again is the RMS value, does not equal to our VR plus our VL, which again, these are both RMS. Okay? And just like our RC circuits, this is due to the fact that these voltages are not in phase with each other, okay? However, if we measure the voltage at any given time, which we can call time t, Kirchhoff's voltage law does hold true, okay? So we can say, however, at any given time, the instantaneous voltages will add correctly. And this is according to Kirchhoff's voltage law, okay? So far, pretty much an exact replica of what happens in RC circuits, okay? So if we were to now look at the phase relationship between the voltages, okay, we can do that in a way of a phase diagram, okay, just like what we did with RC circuits. So just like our RC circuits, we're going to have our voltage of our resistor coming to the right, like so, okay? And also, just like our RC circuit, the current in the circuit is in phase with the voltage of the resistor. So also, just like our RC circuit, if we measure the current at any point in the circuit, the current will be the same at any given point, okay? However, just like our RC circuit, because this is AC, our current is also fluctuating, okay? It's just if we measure the current at a given time and we measure it across different points of the circuit, it's all going to be the same value, okay? And that again is due to the fact that we have a series circuit in this case. The difference between RL circuits and RC circuits is that the voltage across the inductor actually leads our voltage across our resistor and our current by 90 degrees, okay? So this is the voltage across our inductor. And I go through why this is in the previous video in the playlist, okay? Right, so the voltage across our inductor leads the voltage across our resistor by 90 degrees. And so we have another memory tip for this situation right here, okay? Just like the previous memory tip, ICE, this didn't really help me in the exam, but my teacher taught it anyway, so it might help you. So I'm gonna teach it to you now. This memory tip is Eli, okay? And so what this is saying is, in a AC inductor circuit, voltage across the inductor leads current by 90 degrees, okay? So the way this acronym will work, we see our current lags the EMF of our inductor. So if that helps you, sweet. Okay, so coming back to our vector diagram, just like in our RC circuit, in order to add our voltages together, we must do vector addition, okay? So therefore we have our voltage of our resistor coming to the right, and then we have the voltage of our inductor coming up like this, and this resultant vector is the voltage of our supply, okay? And so therefore, in our diagram, the voltage of our supply is going to come up like so. And so therefore, this gives a formula for our supply voltage as Vs squared is equal to VR squared plus VL squared. And so therefore, Vs is equal to square root VR squared plus VL squared, okay? And if we want to figure out our phase difference between the voltage of our resistor and the voltage of our supply, this is obviously this angle right here, okay? And that angle is going to correspond to this angle in our triangle, okay? So as you can see, so therefore, in order to find this angle, we get theta is equal to the inverse tan, opposite, which is our VL, all over our adjacent, which is our VR. And so really the main difference between RC circuits and RL circuits is the fact that the voltage across the inductor leads the voltage across our resistor, whereas in an RC circuit, the voltage of the capacitor lags the voltage of the resistor, okay? So with this knowledge, we can do a practice question. Okay, so an inductor and a resistor is in series in a circuit with an AC supply. The supply has an RMS voltage of 11.5 volts, and the RMS voltage across our inductor is 7.8 volts. And so what we need to do is calculate the voltage across our resistor and also calculate the phase angle between Vs and Vr. Okay, so first, calculating our Vr. If we draw our phasor diagram, we obviously know we're going to have Vr coming across to the right like this, and the voltage across our inductor is pointing straight up and down, okay? And we also know that our supply is somewhere over here, okay? And we also know that this is going to be the phase angle between our supply voltage and our Vr, okay? And so therefore, constructing this into a right angle triangle so we can do some trig, we have our Vr coming here, our VL coming up, and this is our Vs. And this is obviously our angle theta. Okay, and so therefore, in order to calculate Vr, we know that Vs squared is equal to Vr squared plus VL squared, and so therefore, Vr squared is equal to Vs squared minus VL squared, and so therefore, Vr is equal to square root Vs minus VL, and these two values are squared, and so therefore, Vr is equal to square root 11.5 squared minus 7.8 squared, and this gives a Vr value of 8.45 volts, okay? And again, this is the RMS value of the voltage across our resistor, okay? Now, in order to calculate the phase angle, we know that theta is equal to the inverse tan of our voltage across our inductor divided by the voltage across our resistor, okay? Now, do I recommend doing it this way? Actually, no. The reason for this is because we calculated the voltage across our resistor, okay? And so just in case we get the voltage across our resistor wrong, just in case we get that value wrong, okay, we don't want to use this in our second calculation, because if we get this wrong, okay, therefore this is going to mess up this question as well, okay? And so what I recommend doing is using theta is equal to the inverse sine VL all over Vs, okay? This L should be subscript. There we go. And so therefore our theta is equal to the inverse sine VL, which is 7.8 all over 11.5, and this gives a theta value of 42.7 degrees. Okay, now obviously in this case we did get our voltage across our resistor correct, so if you really wanted to, you could figure this out and say 7.8 all over 8.45, and this indeed does give you 42.7 degrees also, okay? Now, to add a little twist to this question, if we were to increase the frequency of our AC supply, what is going to happen to our phase angle, okay? So you can pause the video and have a think about that. If our AC frequency increases, okay, and as we know, the reactance of our inductor is directly proportional to the angular frequency, and because we know angular frequency is equal to 2 pi f, therefore our angular frequency is directly proportional to our frequency, okay? And so therefore we can say that the reactance of our inductor is directly proportional to our frequency. So if our frequency increases, therefore the reactance of our inductor is also going to increase. And because we know the voltage across our inductor is equal to the current multiplied by the reactance of the inductor, if the reactance of the inductor increases, therefore the voltage across the inductor is also going to increase. Okay, and because our supply voltage has not changed, therefore, because the voltage across our inductor has increased, the voltage across our resistor must decrease, okay? And so if we look at our phasor diagram, if we were to copy this down, okay, bring this over here, if the voltage across our inductor has increased, okay, let's make it bigger, so this is now new VL, and the voltage across our resistor has decreased, therefore, our new Vs is going to look something like this, okay? And so as you can see, we have a much bigger phase angle, okay? So our phase angle will increase. Alright, and obviously the reverse scenario will happen if we were to decrease the frequency, alright? And so that will be it for this video. See ya!